In this lesson, we're going to talk about electrostatic potential maps. Now, you're most likely to encounter this topic either in your first or second chapter of organic chemistry. Now, you might be wondering, what is an electrostatic potential map? Well, let's think about the words electrostatic. I think of static electricity. Static means stationary. In this case, the electrons, they're stuck on the atoms being examined. You also have dynamic electricity. Think of electricity flowing through a wire. Now, what about potential? Think of the word electric potential. Perhaps you're familiar with the word voltage. Think of a 1.5 volt battery. Voltage is basically the difference of two potentials. So let's say at point A, the electric potential is 300, and at point B is 500. Voltage is the potential difference between those 2 points, which will be 200. The electric potential at A is 300 volts. The electric potential at B is 500 volts. So B has a higher electric potential than A. So when you think of the word electrostatic potential, think of electric potential in the sense of voltage, but also charge as well. In physics, the electric potential of a charge is dependent on the electric charge. So let's say if you have a positive charge with a Q value of 100 microcoulombs, at a distance of 1 meter away from that charge, it's going to create an electric potential, and we can plug it in this formula. K is 9 times 10 to the 9. Q is 100 times 10 to the minus 6. And at a distance of 1 meter, this charge will create an electric potential of 900 volts. Now, let's say if we double the charge. Instead of Q, let's say it's 2 times the value of Q, or 200. So if we double this number, at the same distance of 1 meter, the electric potential will double to 1800 volts. So as the electric charge increases, the electric potential increases. Now you might be wondering, why am I talking about physics when this topic is for organic chemistry students? Now the reason I mention this is to help you to see that there's a direct relationship between electric charge and electric potential. They're directly related. The electrostatic potential map, it tells us how electric charge is distributed among a molecule. But this map doesn't have the word charge in it. It has the word potential. So the question is, why is that? Now, this map is neatly color-coded in line with the visible spectrum. Think of Worksheet BIV, red, orange, yellow, green, blue, violet. Now, the orange-red areas, that's where you have a region of negative charge. So if you see a molecule that has a red-orange color to it, that's the negatively charged part of the molecule. The blue area represents the positively charged region. So in this way, the electrostatic potential map, it helps you to see how charge is distributed in the molecule. But now remember, charge is related to potential. As the charge increases, the electric potential increases as well. So as you move to the right, the charge density increases. In this case, we could say the electron density because electrons carry a negative charge. So the electron density increases as you move to the right. The more electrons that you have in an area, the greater the charge. Keep in mind, each electron has a charge of negative 1.602 times 10 to the negative 19 coulombs. So if you have 2 electrons, the charge will be negative 3.2 times 10 to the negative 19 electrons. So the more electrons that you have in a region, the greater the charge. And as the charge increases, the electric potential increases. So the color red has a more negative electric potential than the color orange. You have more electrons in the red region, you have more negative charge, and you have a higher negative electric potential. Now going in the other direction, we're going towards the positive charge. So by the way, this V is a negative value. When I mean that it's going up, I mean that it's becoming more negative. I'm going to put some numbers to it soon. So going to the left, the charge increases, but in a more positive way. The electric potential increases. Now, because we're dealing with positive charge, this can mean two things. It can mean that we have more protons, because protons carry a positive charge, or it can mean that we have the absence of electrons. Now, in the majority of cases, protons, they're basically fixed in the atom. The protons, which are found in the nucleus, they don't really move. So when dealing with chemical reactions, it's the electrons that typically move. So in the context of organic chemistry, we could say that the red areas are electron rich. The blue areas are electron poor. We have a deficiency of electrons in the blue areas, given that the protons are basically stationary in the nucleus of an atom. So the areas where it's electron rich, that's the nucleophilic region of the molecule. Nucleophiles are nucleus 11. They are electron rich molecules. They tend to have a lot of lone pairs or negative charge. The electron poor areas, those are the ones with a positive charge or an empty p orbital. Those are the ones that are deficient of electrons, so they're electrophilic. The word phile means loving. So an electrophile, it loves electrons, it wants electrons. It's electron poor, so it really wants it. This video is for those of you who are thinking about joining my Patreon membership program. You can access it at patreon.com/mathsciencetutor. Now we're going to focus on the organic chemistry post, so if you were to click this link, my organic chemistry videos will show up. Now this video that you see here, this is the extended version of my organic chemistry basic introduction video. The free version on YouTube, it's about 41 minutes long. And you can get the direct link to the extended version if you check the description section of this video. But the full version, it's an hour and 42 minutes long. You can access the full version on Patreon or in my YouTube membership program. The advantage of Patreon is that I can upload worksheets to it, which I can't really do on YouTube as of now. So here's some other videos that I have for organic chemistry: hybridization, resonance structures, acids and bases, functional groups, IUPAC nomenclature, Newton projections, chair conformations. Now the worksheets, I haven't made them yet at the time of making this video, but they are coming soon. So feel free to check this post later to see when it becomes available. The same is true for this practice test. If you see the words coming soon, that means that I haven't finished making them yet, but they are coming soon. For practice test 1, this is going to cover the first 4 chapters of organic chemistry. I'm going to have stereochemistry, specific rotation, SN1, SN2, E1, E2 reactions. Now I do have the test review for this. I don't have the worksheet yet, but here is the test review, which contains 77 practice problems. The worksheet contains all of the problems that are found in the extended version of that video. Now the worksheets are for those of you who want to print out of all the practice problems. Perhaps you want to work through them while you're in class or in school at the library or somewhere. But since many of you have requested it, I've decided to make worksheets for many of my extended videos. Now I do have some other videos on alkene reactions, alkyne reactions, This is practice test 2. Practice test 3 covers alcohol reactions. It's going to cover radical reactions and spectroscopy. Now I have my Organic Chemistry 1 final exam review video. This video is about 6 hours long. The free version on YouTube is somewhere between 1 and 2 hours long. And the worksheet, I don't have it yet, but that's coming up as well. Next we have spectroscopy. Let's load this up. Ethers, epoxides, deals all the reactions, carboxylic acid derivatives, aldehydes and ketones, electrophilic aromatic substitution reactions or benzene reactions, and other stuff as well. And I also have my Organic Chemistry 2 final exam review video. So there's a lot of stuff that you'll get if you decide to join my Patreon membership program if you're taking organic chemistry. So feel free to take a look at this when you get a chance, and thanks for watching. Now let's put some numbers to this graph just to really help you to see the value of this tool. So the middle area, that is the green-yellow area, this area is neutral. So think of it as 0 on a number line. It has a charge value of 0, meaning you have an equal number of protons and electrons, so it's electrically neutral. And if there's no charge, there's no potential. The electric potential is 0. V is equal to K Q over R. So if Q is 0, V is 0. Now, as we get closer and closer to the red side, it becomes more negative. So Q might be, I'm just going to put a number here, it might be negative 100 microcoulombs. Over here, Q might be negative 500 microcoulombs. So at this point, the potential might be negative 200 volts. Well, let's just say negative 100 volts just to keep things simple. And over here it might be negative 500 volts. So as you move towards the right, the electric potential is becoming more negative. So you could say the absolute value of V is increasing, but V is really decreasing if you look at negative values as being lower than positive values. But the absolute value of Q is increasing, but the real value of Q is becoming more negative. So I just want to clarify that point. So the arrow that's going down, it just means that they're becoming more negative. Now on the other side, let's say this light blue region, Q is going to be positive. So it might be positive 100 microcoulombs. And the electric potential is going to be positive 100 volts. As we get to the more darker blue areas, it's going to be even more positive. So this might be positive 500 microcoulombs with an electric potential of positive 500 volts. So I want to help you to see the numbers here. So just to recap, as you move to the right towards the red area, it becomes more negatively charged and the electric potential is decreasing. It's becoming more negative. As you move towards the left, towards the blue areas, the charge is increasing in a more positive way and the electric potential is also positive. So the potentials are high at either side, but in the middle it's 0. On the right side it's negative, on the left side it's positive. Now let's work on a practice problem. So here we have electrostatic potential maps of different molecules and ions on the right side, and we want to match it to the appropriate substance. So how can we do this? Remember, red represents negative, blue is positive, green is neutral. So looking at the molecules that we have, we know that HF and water are polar. When you're dealing with polar molecules, you have one side is positive, one side is negative. So that means you're going to have blue and red there. Hydrogen is nonpolar, which means it's neutral. So we should expect hydrogen to have the green color. Therefore, this should be H2. We don't see two different colors. So because we see one color, it's nonpolar and it's neutral. There's no separation of charge. So number 2 is B. Now let's focus on the last two, H3O plus and hydroxide. We know that positive charges correlate to a blue color. Negative charges correlate to a red color. Now we're dealing with ions, particles with a net charge. So because H3O plus has an overall net positive charge, we should expect that the entire particle, for the most part, should be predominantly blue. Hydroxide has an overall negative charge, so we should expect that the entire particle will be mostly red. So looking at all our options, D is mostly red. That's going to be hydroxide. E is for the most part blue, and that's going to be H3O plus. And of course, we can see that there's 4 atoms here, so that's going to indicate that it's H2O plus. It's the only option with 4 atoms. So number 5 is D, and number 4 is E. Now what about number 1 and number 3? HF and H2O, they're polar molecules. Polar molecules, you're going to have 2 colors, or at least 2 predominant colors, red and blue. So looking at HF, fluorine is partially negative. So this is going to be the red side. And hydrogen is partially positive. That's going to be the blue side. Now if we focus on water, I'm going to draw it out. That's water. Oxygen is electronegative, so it's going to carry the partial negative charge. It's going to be red. And hydrogen is going to be partially positive, blue. And looking at the shape of this molecule, we can see 2 blue regions. That's the 2 hydrogen atoms. And we could see the red region, which is the oxygen. So C has to be water. For A, this has to be HF. So the red region represents fluorine. The blue region, notice that it's smaller here, that's hydrogen. Now let's summarize what we've learned as it relates to polarity. Nonpolar molecules, they tend to have basically one color, like a greenish yellow color. As we saw in the case of hydrogen, we didn't see 2 distinct colors, basically one color. And around the yellow-green area, we know that the potential is 0. That's the region where it's electrically neutral. So you don't really have separation of charge, as in the case of a polar molecule. So when dealing with polar molecules, like HF, we saw 2 major colors, a red area and a blue area. The blue area was for hydrogen, and the red area was mostly for fluorine. Now, of course, there was some yellow and green in between, but for the most part, if you see one side red and the other side blue, that's an indication that you're dealing with a polar molecule. One side is partially positive. In this case, that's the hydrogen side. And the other side is partially negative. Now, the other part has to do with ions. So if you see an overall blue color, that means you're dealing with a positively charged ion. If you see an overall red color, or orange red, the more red it is, the more negative it is. You're dealing with a negatively charged ion. So hopefully this will help you to distinguish a polar molecule from a nonpolar molecule from an ion using electrostatic potential maps. Now let's consider the electrostatic potential maps of hydrogen, methane, and ammonia. Now when you see green or yellow-green, for the most part you're dealing with nonpolar molecules. When you see clear distinct colors of red and blue, you're dealing with polar molecules. The red area has a very high negative electric potential. The blue area has a very high positive electric potential. When you see green and yellow, the electric potential is more closer to zero, rather than being far apart either in a positive side or in a negative side. Now when we look at hydrogen, hydrogen has an electronegativity value of 2.1. So the electronegativity difference in this bond is 0. Now when we focus on methane, particularly the carbon-hydrogen bond, the EN difference is not 0. Carbon has an electronegativity value of 2.5, and for hydrogen it's 2.1. So we have an EN difference of 0.4. In order to have a polar bond, the electronegativity difference is defined to be 0.5 or higher. So the CH bond is just below that threshold. Now for a polar molecule, like ammonia, there is a significant difference. Nitrogen has an electronegativity value of 3.0. So we have an EN difference of 0.9. So we can see why ammonia is polar. So looking at hydrogen, we could see why, for the most part, it's virtually a solid green color. We don't see separation of colors here. We basically see, for the most part, one distinct color. And the reason being is there's not much electronegativity difference between the two hydrogen atoms. For methane, there is a small difference, and we could see some color variation. We could see the hydrogen is more on the green side, whereas the carbon, it's a little bit more electronegative. We could see it's a different color. It's more on the yellow side. Now going back to our electrostatic potential spectrum, we have red, orange, yellow, green, and blue. Now remember, blue is positive and red is negative. So when you're dealing with red and blue, you're dealing with a polar molecule. You're dealing with a more polar molecule, so to speak. When you're dealing with yellow and green, that's closer to the middle, you're dealing with a less polar molecule, or even a nonpolar molecule. So hydrogen is green, and the carbon is more on the yellow orange side. Let's put yellow for carbon. So green is more positive and yellow is more negative. As we can see, green is more on the positive side, yellow is closer to the negative side. And that's what we see here. So just to recap, if you see a molecule with one side red, one side blue, you're dealing with a highly polar molecule. If you see just one uniform color, either yellow or green, you're dealing with a nonpolar molecule. If you see like one region green, one region yellow, Either it could be a nonpolar molecule, like a CH bond, or it could be a slightly polar molecule. So hopefully that helps you to see how you can use electrostatic potential maps to not only identify molecules, but to determine if you're dealing with a polar molecule, a nonpolar molecule, or even an ion.